Welcome to Chapter 4, Eukaryotic Cells and Microorganisms. History of Eukaryotes. The first eukaryotic cells appeared a very long time ago, 2 to 3 billion years. Bacteria, archaea, and eukarya are all evolved from the last common ancestor. First primitive eukaryotes were likely single-celled and independent, and over time cells aggregated and they formed colonies. So I just want to remind you that we're talking about eukaryotic cells, cells that are most like ours, our human cells. We had talked about bacteria and archaea, and remember those fall under the umbrella of prokaryotes, which your book has not mentioned yet. At least I don't think it has. So many times you'll hear me talk about prokaryotes versus eukaryotes. And remember that prokaryotes include bacteria and archaea, and eukaryotes are more like us, cells that are similar to ours or ours itself, and therefore any microorganism that falls under the umbrella of eukaryotes, eukaryotes, are much more difficult to treat because those cells are so much like ours and the parts of the cells are so much like ours. So moving on. So eukaryotes, appendages from moving eukaryotes include cilia and flagella. So when we talk about eukaryotic flagella, they're different from bacteria flagella. They're thicker, more complex. The eukaryotic flagella that you may be aware of is the flagella from a sperm. When we talk about cilia, eukaryotic cilia, it's similar to the flagella in structure, but they're small and more numerous, so they're like little finger-like projections coming off of the surface of the cell. They're found only in a single group of protozoa and certain animal cells, these cilia. So Glycocalyx, outermost layer that comes into direct contact with the environment, the Glycocalyx, like the bacterial Glycocalyx, the eukarya Glycocalyx is also composed of polysaccharides, appears as kind of like a network of fibers or a slime layer or a capsule. So what's the point of the Glycocalyx? It contributes to the protection, the adherence or the sticking, and the signal reception of the cell. So we'll learn more about that later on in the semester. So the cell wall of eukaryotes or eukaryote cells, protozoa and helminths do not have cell walls. So I turned that a different color, bolded part of it, underlined part of it, so you remember that, because I'm pretty certain that that is a test question. Protozoa and helminths do not have cell walls. However, they fall under the umbrella of the eukaryotes. That's what we're talking about here in this chapter. Fungi also falls under the umbrella of the eukaryotes. However, fungi do have cell walls. So remember, a cell wall is like an additional part. It's not referring to the cell membrane. But we'll get to more of that later. So cell walls of fungi, they make the cells more rigid, provide some structural support and shape. There's a little bit different chemical composition in fungi from bacterial and archaeal walls. There's a thick inner layer, and that layer is composed of what we refer to as chitin, or it might be composed of cellulose. Just depends on what cell we're looking at. So here's a picture. So make sure that you remember that when we're talking about fungi, okay, we're talking about fungi here, and we mention chitin or cellulose, that you remember that these two things, the inner layer part of that cell wall of fungi is made up of chitin or cellulose. I'm pretty sure that's a test question too. So you can see here's a picture. These are different type. This is a type of fungi, and you can see they're showing this expanded. So you can see there's some glycoproteins, some glycans, cell membrane, and then underneath that is the chitin, as well as, well, actually this is outside, this is inside, I got that backwards. So the glycocalyx is outside. Moving on to the cell membrane of the eukaryotic cell, typical bilayer, the one that you're familiar with. There's, fatty acid tails and polar heads. Typical bilayer of phospholipids in which protein molecules are embedded. So not only do they have the fatty acid tails and polar heads, there's also some proteins that are embedded in the cell membrane. In addition, there's some sterols of various kinds, which contribute to the rigidity and stability of the membrane. And these sterols are important in cells that do not have a cell wall. So it's important for the structure, the stability of that structure. Cytoplasmic membranes of the eukaryotes have similar function as those in bacteria and archaea, as serving as selectively permeable barriers. So some similarities there. Okay, we get into the nucleus, most prominent organelle of the eukaryotic cell, separated from the cell cytoplasm by an external boundary called the nuclear envelope. So when you think of the nuclear envelope, think of it as the boundary around the nucleus. It's composed of two parallel membranes, the lipid bilayers, and then separated by a little bit of a narrow space. There are some perforations with some pores where the formed at sites where the membranes unite. And then certain macromolecules can kind of go in and out through those pores. The nucleus, when we get into that nucleus, there is also a nucleolus. And I can say that this is probably one of the most missed questions on the test is, where are ribosomes made in these cells, in these eukaryotic cells? It's in the nucleolus. The nucleolus is within the nucleus. It's like another kind of circular entity, we'll say, in the nucleus. We refer to it as the nucleolus, and that is the site for ribosomal RNA synthesis, which means that's where RNA is made. In addition, in the nucleus, you'll find the chromatin. That is made of DNA and histoproteins. And keep in mind that histone proteins actually help to coil up the DNA. So those histones, which are proteins, help to coil up that DNA when the time comes. And of course, the chromatin is the genetic material of the cell. So you can see here's an image of a nucleus and the nucleolus. You can see the boundary around the nucleus. We refer to it as a nuclear envelope. You can't really see the nuclear pore, but it's like a little opening. You can see them in this picture here, these little pore-like things. And you can see the endoplasmic reticulum butted right up against the nucleus, okay, in this picture. So you have your nucleus is the circular object, the nucleolus is within the nucleus, and then the endoplasmic reticulum is right up close to the nucleus. And that's an important thing to remember as we move forward with this. Internal structures, we have the endoplasmic reticulum, as we mentioned, the ER. It's a series of membrane tunnels used to transport and store different items that are made in, sorry, I don't know what just happened in my kitchen, but I think the house just fell down. Let me start over. So the internal structures, one of the internal structures is the endoplasmic reticulum, and I'm abbreviating that as ER, okay? And that is a series of tunnels used to transport and store certain things that are made in the cell. So we're talking about rough ER. That allows transport materials from the nucleus to the cytoplasm and all the way out to the exterior of the cell. And there are, as we already know from AMP1, ribosomes that are attached to its surface. So the rough ER the name is rough ER because they are kind of like studded, or I refer to it in A&P as bedazzled, right? If you know what bedazzled is, then you might get a kick out of that. If you don't, then just know that it's like studded. It's like little bumps all over the endoplasmic reticulum. And those bumps are the ribosomes. We also have smooth endoplasmic reticulum, SER, and that is a network without ribosomes, a tubular network without ribosomes. And the smooth ER functions in nutrient processing and in synthesis and storage of non-protein molecules, macromolecules such as lipids. So the rough ER focuses on the transport of materials specifically to proteins. The smooth ER, other things other than proteins, specifically lipids. So you should associate rough ER with proteins and smooth ER with lipids. All right, so this picture is, I feel like this is new this semester with this new edition of textbook, because when I saw this, I kind of was drawn into it. And I think it's interesting the way it's shown. You can see that you have the nucleus here, and then you have the ER, the rough ER coming off. But when you look at this really closely, it shows you how those ribosomes are embedded into the rough ER, or into the ER, I could say. And you see that it's, here's the ribosome, and it's reading the mRNA, right? That genetic code. And as it's reading it, it's making the protein that's being synthesized. And you can see that it's just kind of pushing it off into, the out of, we'll say the, my words, the cistern. Pushing. It's right there. It's right in front of my face. So I just thought this picture was interesting, the way it's illustrated. So it's a good one. It's a good picture. So more internal structures, the Golgi apparatus, the site in the cell in which proteins are modified and then sent to their final destinations or packed and shipped. And I just want to back up here, because one of the things I forgot to point out, because I think my house blew up on the other side, is that when I talk about ER, think of ER as the conveyor belt in the warehouse, right? It's the conveyor belt in the warehouse when you're making, a product. And then when we jump over here back to Golgi apparatus, it's where the item or the product is packed and shipped, right? So when we think of the Golgi apparatus, it's finally packed and put into the trucks and sent to where it's going to go. So when it says the site in the cell in which proteins are modified and then sent to their final destinations, think of Golgi apparatus. So the Golgi apparatus consists of flattened disc-shaped sacs called cisternae. These are always closely associated with the endoplasmic reticulum, the Golgi apparatus. There are transitional vesicles from the ER that are picked up at the face of the Golgi apparatus. Proteins are modified within the cisternae by the addition of polysaccharides and lipids. Condensing vesicles pinch off the Golgi apparatus and are then conveyed to the lysosomes or transported outside the cell. So here's kind of everything together. You can see as the ER is letting things go, as things travel through the ER from the nucleus, they're kind of, stored a little bit. They're put in a vesicle, and then they are transferred over to the Golgi apparatus. And then the Golgi apparatus basically loads them up in the truck, these vesicles, and sends them on their merry way to where they are needed for the cell. Different proteins, or depending on what we're talking about, it could be lipids, depending on where we're at. So to finish this off, nature's assembly line is the nucleus, the ER, and the Golgi apparatus. So a segment of DNA containing the instructions for producing a protein is copied onto RNA, and this RNA transcript is passed out through the nuclear pores directly to the ribosomes in the ER. Specific proteins on the rough ER are deposited in the lumen and transported to the Golgi apparatus, and then those proteins in the Golgi apparatus are chemically modified and packaged into vesicles to be used by the cell. So that's the end of part 1, and we'll pick up on part 2.